Hello, my name's Wayman Kwan. In this video, I'm going to start talking about exponent laws. More specifically, some introductory items to understand what are exponent laws. So in this video, I am going to cover the following items. The first thing is, I'm going to explain what is an exponent. The second thing is, we're going to go and try to convert numbers into what we call exponential form. What is this exponential form? A little hint. It is the form of prime factorization, how we factorize numbers and how we write it in a clean way. The third point is, we're going to go with the technical stuff with exponents, such as what happens with terms and multiple bases and exponents. What about negative numbers and exponents? What happens to them? I'll go through some of the technical details with exponents. Finally, I'm going to introduce some of the basic exponent laws. They're really properties of exponents, but you can think of them as basic laws. Now, to the first question. What is an exponent? Now, note how this 5 is written with that 2 on the top right as really small. Now, in terms of how we define these things, this big 5 is affected by this little 2. This 5, we can consider this as the base. And you'll see why we call this the base. This little 2 here is what we call the exponent. It is written exactly the same way. Now, what does this mean? The exponent tells us how many times we multiply the base. So if the exponent is 2, that means 5 is multiplied 2 times. So 5 to the 2 means 5 times 5. Let's see another example of this. What does 6, 3 means? The first thing is we gotta identify what is the base and what is the exponent. So the base in this case is the 6. It's always the bigger number. The exponent is always to the right and always to the top of the base. In this case, the exponent is 3. What does this mean? That means the 6 is multiplied 3 times. So this is equal to 6 times 6 times 6. Now, it is important to note that 6 to the 3 is equal to 6 times 6 times 6. So this is what we call, we're really expanding our exponential form. But we can actually go the other way because they are equal. Let's take, for example, 7 times 7 times 7 times 7. How can we write this using exponents? So we see that there are 4 7s. So we know that there's going to be exponent 4. Because we're multiplying 7 4 times, our base is 7 and the exponent is 4. Writing things in exponent form is actually pretty neat. It actually makes math a lot cleaner instead of repeatedly writing 7s all the time. This is really cool, and you don't want to be writing lots of things. Math is supposed to be a clean subject, which is why writing things in exponential form is really cool. Now, just a little reminder, you have to make sure that things are actually multiplied to one another, not adding. So if we have 7 plus 7, it doesn't mean 7 to the 2. It is not a plus operation. It is always a multiplication operation. Just be careful of that. So this is not true at all. Let's move on to the next idea. Let's break down numbers in what we call exponential form. What do I mean by that? It means that we want to find a way to write numbers in its prime factorization in a clean way. And we are going to use exponent to show that. For example, let's start with 81. How can we break down 81 into its prime factorization? Well, if you haven't noticed, 81 is actually equal to 3 times 3 times 3 times 3. If you don't believe me, 3 times 3 is 9, times 3 is 27, times 3 gives 81. That's awesome. Now, can we actually simplify this using exponents? Yes, we can. Notice how we have 4 3's. So our base, in this case, will be 3. And because there are four 3's, that means our exponent is 4. So 81 is 3 to the power 4. Really nice, simple. Great for exponent laws. Now, let's see 400 as an example. How can we break this down into prime factorization? Well, 400 is actually equal to 16 times 25. Let's ask ourselves, is 16 a prime factorization? No. How can we break down 16? 16 can be written as 2 times 2 times 2 times 2. Similarly, 25 is not prime factorization. In fact, it's not prime. We can break down 25 into 5 times 5. Now, since these two numbers are multiplied one another, that means that the 2's and the 5's are all multiplied one another. Excellent. Now, we've broken down 400 into its prime factorization. But can we clean this up and make it more awesome, more concise? Yes, we can. And we will use exponents to leverage that fact. Now, are there any numbers that are multiplied and that are the same? Yes, we see a bunch of 2's. In fact, we have 4 2's. So we can rewrite the 4 2's as 2 to the power 4. Now that is multiplied by 2 5's. And we can rewrite this as 5 to the power of 2. And that is our prime factorization in its cleanest form, and that's equal to 400. This is neat. Now, notice that we have 2 bases and 2 exponents. Now, the question is, how do I know which exponent affects which base? I'm going to get to that question a little bit later, which is in 2 minutes. But before that, I want to explore one idea before we get to these multiple bases, multiple exponents. And that is the idea of using algebra. Now, what happens if we have a variable for a base? Example, we have a to the power of 5. Thus our definition completely blows up because we have a variable as a base. No, it doesn't. It means exactly the same thing. So in this case, the a, which is our variable, is the base, and 5 is the exponent. That means that this expression can be expanded to a times a times a times a times a. Absolutely nothing wrong with that. Vice versa, going the opposite way, if we see we have x times x times x times x, we see that we have 4 x's, and that's multiplied 4 times. So we can rewrite this as x to the power of 4. Nothing wrong with that. So we could use whatever base we want. A variable, a fraction, a decimal, a square root number, anything except for complex numbers, of course, which I'm not going to talk about. We can use any number, and this idea of exponents will not go bust. So that's true for the base. what happens if, let's say, we have a variable or a fraction for the exponent? We are not going to talk about it in this video. We'll talk about it in a later video, but that is something to consider. If our base is anything, we are very fine. But what does it mean as an exponent, as a fraction? That is for another video. Now, let's get back to our question that we mentioned previously with multivariables and exponents at the same time. And we come to this example with numbers and exponents. Now, let's take a look at our first example here. We have 6a exponent 5. The natural question is, what is the base? Is it 6? Is it the 6a? Is it 5 that is the base? The most important thing to recognize is that the base is always to the immediate left of the exponent. So in this case, the base is the letter A because the 5 is immediately affecting the A. However, it does not necessarily affect the 6 here. Now, a little hidden secret is that, technically speaking, we can write 6a to the 5 as the following. 6 times a to the 5. And now you actually see that 6 is not really part of the base. We kind of separated them. So we have the number term and we have the variable term. If we were to expand this further, a to the 5, it gives 6 times a times a times a times a times a. And 6a to the 5 means 6 times a 5 times. And that's how we expand this properly. Similarly, let's see 25x to the power of 3. What is the base? The base in this case is the x, and it's not the number. This 3 only affects this x here. So we can rewrite 25x cubed as 25 times x cubed. Little hidden secret again. When you have a number multiplied by a variable, or when there's nothing in between, it's as if it is multiplying. And if we were to expand x to the 3, this becomes 25 times x to the 3. My apologies. Let me erase this. So that becomes x times x times x. Now, if we were to really expand this completely, we can break down the 25 as 5 times 5 times x times x times x. Because 25 is equal to 5 times 5. That is if you really want to fully expand everything out. Now, that's how we deal with numbers and exponents, where there's still a number, which we think of it as a separate thing that's multiplied, attached to the variable here. Now, what happens if we really have two variables and two exponents at the same time? How does that affect how we expand exponents? Let's take our first example here. 2 to the 3, 3 to the 4. How does that work? Now remember, the exponent only affects the base, which is to the immediate left of the exponent. So in this case, this 3 here only affects this 2. And this 4 here only affects this 3. And remember, if we were to really break this down, this means it's 2 to the 3 times 3 to the 4. Remember, there's an invisible multiplication when they're attached this way. If we were to expand this out, this will become 2 times 2 times 2. And these two things are multiplied together. So there's a multiplication here. That becomes 3 times 3 times 3 times 3. And that's how we properly expand 2 to the 3, 3 to the 4. Now, what about a to the 3, b to the 4? Exactly the same idea here. This 3 only affects this a here. So let me draw again. And this 4 only affects this b. This 4 does not affect this a because that's not the base. Remember, the base is always to the left of whatever the exponent is. Or in other words, if the base is in the middle, the exponent is always to its immediate right. Now, if we were to expand this, a to the 3 means a times a times a, and b to the 4 means times b times b times b times b. There's an invisible multiply, which is why this is also multiplied. And that's how we really think about multiple exponents on multiple base. Oh, the exponent is always to the right of the base, and the exponent only affects the base that is to its immediate left. Now, what happens when we have brackets and exponents? Let's take this example. Now, if we have open bracket x, close bracket to the power 2, how do we write this? Now, if we have everything in brackets, so I've underlined everything, it means that whatever is inside this bracket, it gets multiplied twice. Because it's whatever completely inside of the bracket gets multiplied by the bracket and the exponent on the outside. So, x power 2 means x times x. And if we were to really simplify this, this literally simplifies to x times x. That's a simple example. What about a more complex example? Let's say open brackets 3x, close bracket to the 4. What does this mean? This means that whatever's inside the bracket gets multiplied 4 times. So our base in this case is 3x, and that's get multiplied 4 times. So this is equal to 3x times 3x times 3x times 3x. Now, I'm not going to simplify this a little bit further. We can massage this so that it looks cleaner, but we'll leave it as that just to get the key idea of what happens when we have brackets and then the exponent on the outside of the brackets. It's whatever that's inside gets multiplied repeatedly. Which brings us to one of the most important points and confusion about brackets and exponents. And that is dealing with negative numbers. Now let's take a look at these two examples very carefully. On the first one, we have open bracket, -3, close bracket to the 2. On the second thing, we have the negative on the outside, open bracket, 3, close bracket to the 2. Do they actually have the same answer? Absolutely not. And here's the reason. Let's take a look at the first one carefully. We see that -3 is all in brackets. So this 2 affects everything inside this bracket here. So this means -3 times -3. -3 times -3 gives 9. So the first one gives 9. The second one, it's a little bit tricky. Notice how we have a negative outside of the bracket and then we have an open bracket. How do we think of this? This, you can think of it as there is a -1 in front, and then that's multiplied by whatever's inside the bracket, so that becomes 3 to the power 2. If we were to expand this carefully, this will become -1 times, inside the bracket it's 3, so it's 3 times 3. Notice how I'm still using brackets because it is the entire inside bracket that's multiplied itself twice because of the exponent. If we were to simplify this expression, this gives -9. Very interesting. So, what does that mean? If that negative is part of the inside, we notice that it gives +9. But if there is the negatives part of the outside of the brackets, it gives -9. I hope I showed you the reason why, and I hope this is clear. So, in an exam, make sure you do not make this mistake. Here's the next question. Are these two exactly the same? And we're going to really think about why the idea of exponents is interesting and why we are using multiplication. Now, are these actually the same thing? Well, let's expand both terms out. Now, on the first term, we have a to the 2, b to the 3. So that gives us a times times b times b times b. On the second term, we have, well, let's expand this out. It gives b times b times b times a times a. Now, looking forward, it doesn't look like the first one and the second one seems to be the same thing. Now, what is the operation that's holding all of these together? It's multiplication. And in multiplication, we have something called the commutative property. If we have a times b, that is equal to b times a. In other words, we can flip whatever is multiplied one another, and they'll still be exactly the same. Now, if we take a look at the terms we have a times b times b times b, and the second one is b times b times c times a times a. They're just in different order, but they have exactly the same variables and the exact same number of times they multiply each other. So on the left one, there's 3 b's. On the right one, there's 3 b's. On the left one, there's 2 a's. On the right one, there's also 2 a's. So in fact, because they're all multiplied, and because of the commutative property, these two are actually exactly the same. So these two are what we call like terms. So do not get fooled by the order of, the variables. Make sure that they all have the same multiplication. And don't get fooled in a test if they swap the order, because they are actually still are technically the same terms. Finally, let's talk about some of the very basic exponent laws or properties. Now, the first thing is, what is 1 to the power of n? So, n in this case is really what we call an integer. We're not going to use fractions. So n is like 1, 2, 3, 4. So like 1 to the 3, 1 to the 7, 1 to the 100. What is 1 to the n? Well, let's expand this out. So that becomes 1 times 1 times 1, and then we keep going until we get to the last one. But what do we know about multiplying ones? When we multiply ones, it keeps giving 1. So no matter how many ones we multiply, it will keep giving 1. So actually, the final answer of this is actually 1. So if we have the base of 1 and goes to any exponent, it will give 1. Finally, we have a to the 0. What the heck does that equal to? A to 0. What can we think of a to 0? Remember, exponent means that we multiply the base a couple of times. Note, multiply. But if we have 0, that means we are technically multiplying nothing. It means that we have just the identity. But what is nothing in terms of multiplication? If you think it's 0, it is not 0. It is actually 1. So anything to the power of 0 gives exactly 1. We'll explore this idea once we have some operations of exponent. For the time being, just take it as it is. Anything to the 0 gives 1. And this concludes the first video on exponent laws, which is an introduction. If you like this video, feel free to press the like button. If you have any comments, feel free to write them below. Thanks for watching this video on exponent laws and introduction, and I hope to see you again next time.